There are several types of a to d converters, and one of the more common ones is the successive approximation a to d. Now the whole purpose of the analog to digital converter is to take a voltage and convert it to digits. And we have on the analog side V reference low and high, and the voltage input must fall within this range. If it doesn't, it can actually do damage to the a to d converter. Now to figure out what the voltage input is, it's going to set this bit to 1, which is going to break our range into 0 to just below 8 and 8 to 16. If it's in the range of 8 to 16, this bit will remain a 1. If it's in this range of 0 to just below 8, it's going to be a 0. And since it's 7, it's going to then change to a 0. The next thing we do is we set this bit to 1, which breaks this range to 0 to just less than 4 and 4 to just below 8. So if it's in the range of 0 to just below 4, it's going to be a 0. If it's between 4 and just below 8, it's going to be a 1. In this case, it's going to be a 1 because 7 is in that range. This is then going to break that into two ranges from 4 until just below 6 and 6 all the way to 8. If it's in the range of 6 to 8, which it is, it'll remain a 1. Then this last bit will break that last section into two sections. It's going to go from 6 to just below 7 and 7 to 8. And since it's in the range of 7 to 8, this will be a 1. So our value will be 0, 1, 1, 1, which will be the digital value for this voltage. Now a couple of things that you'll notice in here, that this is 7 volts as an integer, but that makes it just easy for our calculations. In reality, voltages will be things like 7.000 and so forth, and at that point you'll find that anything from 7.000 to 7.999 will generate a digital value of 0, 1, 1, 1. Now if we take a look at a value that comes out of a 16-bit a to d like the one we have in the Freedom K64, if we happen to have a value of 1, 1 with all zeros, that means we have 1. This one is half the value, a quarter, an eighth, a 16th, a 32nd, and so on down to 1 over 65,536 of the value. So we really just have 1 half plus 1 quarter, and 1 half plus 1 quarter is 3 quarters or 0.75 times 3.3 volts, and that's how we can work out that the value here would be 2.745 volts. However, if we had all of these as ones, where we had halves, quarters, eighths, all the way down to 1 over 65,536, the fraction that we would get wouldn't be 1. It'd be fairly close, and when we multiply it, we get 3.299995, which is fairly close to 3.3, but it isn't exactly 3.3. In fact, if we were to use our 4-bit a to d up here, the value that we would get with half, quarter, eighth, and 16th would be 0.9375 times 3.3, which would be 3.09 volts out of 3.3. So the more bits of resolution that you have, the closer you're going to get to representing the input voltage, and also you'll be able to get closer to the maximum input voltage that you have on V reference high.